Good afternoon. I'm pleased to introduce Bruce Moyer, Corporate Fellow at Oak Ridge National Laboratory. I first met Bruce when we were working together on an article on his work for the ORNL review. Bruce is specialized over his 43-year career in both fundamental and applied aspects of separation science and technology, especially in the chemistry of solvent extraction and ion exchange using principles of molecular recognition. He will speak on past and present successes in separation science and technology at the lab. He earned his BS degree in chemistry from Duke University and a PhD in inorganic chemistry from the University of North Carolina at Chapel Hill. In 1979, he joined ORNL, where he has provided leadership on the chemistry of extracted separations, tank waste cleanup, nuclear fuel recycle, and critical materials. His work has produced over 250 open literature publications. He has received 17 patents and numerous awards, including the DOE Secretary of Energy Award in 2013 and the Glenn P. Seaborg Actinide Separations Award in 2019. He also serves as co-editor of the journal Solvent Extraction and Ion Exchange, as well as of the book series Ion Exchange and Solvent Extraction. So you have some idea what he's going to talk about here. Please join me in welcoming Dr. Bruce Moyer.
Thank you, Carolyn, for that nice introduction and for the invitation to speak here. It's a real delight. So what I'd like to tell you about is what Carolyn just explained. Are some highlights from my career in separation science and technology, but also in the context, the greater context of the lab's accomplishments. And it's quite humbling in that regard because the lab has some awesome accomplishments in separations since all the way dating back to the Manhattan Project. Okay, so let's see if I can make this advance. First of all, to recognize my mentors, which some of whom you might know, Jack McDowell, Charlie Coleman, and Charlie Bays. I came into Chemtech division, and which then was transferred over to chemistry division. And these were my bosses who taught me a lot over the years about solvent extraction, various extractants and how they function, and many applications that are possible using solvent extraction. Charlie Bays taught me a lot about how to model and understand solvent extraction processes, which then gave me the kind of insight that was needed to advance processes into the real world. Okay, we have a lot to be proud of in the way of solvent extraction and separation science and technology in general at Oak Ridge National Lab. And in this way, we've changed the world, and we're still doing so. I'm going to start with, well, we're going to have two sections to the talk. I'm going to tell you my story, and then broaden it out to the greater picture of separation science and technology at the lab. So let's start with my big story. I've always thought that fundamental research and applied research flourish in synergy. Basic research producing some really good ideas and concepts leading to applied research and testing, and that in so doing, developing new processes. As many of you know, when you try to do something in the real world, things don't always work like you thought, and that generates new questions that are then stimulating fundamental research again, and the cycle goes around. Okay, the big problem that motivated what I'm going to tell you about in the first 2/3 of this talk was related to tank waste cleanup, to clean up the legacy Cold War nuclear waste that had arisen from reprocessing spent nuclear fuel for weapons production. That generated about 100 million gallons of waste, that's most of which is still being stored in underground tanks at Hanford Site and also the Savannah River National Lab. This diagram shows two kinds of tanks, but actually there are really three layers, and these three layers are pretty much all the tanks. There's when they reprocess the fuel, they dissolve it in nitric acid, remove the plutonium and uranium, and the result is high-level waste. And it's highly acidic and contains all the fission products and some actinides and truths. And so that all gets precipitated upon over neutralizing the solutions with sodium hydroxide. That drops out all the higher valent metal ions that forms this sludge that ends up being about 10 to 15% of the mass of the tank waste. The rest is really just salt that from the neutralization, and so it's mostly alkaline sodium nitrate with a bunch of other salts in there. Over the years, they evaporated a lot because they just needed to create more, effectively creating new tank space by evaporating the existing waste. So there's supernatant salt solution and salt cake. That is mostly alkali metal salts, and most of the radioactivity in it is cesium-137. About 98 to 99%, with traces of strontium-90 and some actinides. So at the two sites, what to do with the salt waste? Very similar kinds of ideas. The radionuclides in the salt waste are only about 0.01% of the mass of that waste. So, you know, you'd really like to just remove that and put that into glass, and then the remainder dispose of quite cheaply in cheap waste forms. So that's what this diagram depicts. The salt waste undergoing separations, aiming at removing the soluble cesium, strontium, and trace actinides that are there. The radionuclides then would go into the vitrification, and the remainder then goes into cementitious waste form called saltstone at the Savannah River Site. Hanford does something similar to this, although they decided out there they're going to vitrify everything. They always want to make everything more expensive, I guess. But very similar ideas to decontaminate most of the salt. All right, so that's what we're looking at, is the cesium, strontium, and actinide separation. The latter two, strontium and actinides, Savannah River already had. Let's see, I need you to go back. I keep accidentally clicking here. Go back one more. Okay, so the Savannah River, they 49 tanks. They had 49 at the beginning. They've gradually been reducing the number of tanks. Status about 2008 was 35 million gallons of high-level waste, 420 megacuries eliminated. That's 37 volume percent of the total inventory in DOE system, and over half the curie content. Okay, that's the problem. And this is the same slide, but in pictures. So you can see a picture of the waste there, and the waste tanks in construction, then going to the saltstone vault in the Savannah River after decontamination, the high-level waste, waste form for silicate glass, and empty canisters. Okay, now this slide is going to be busy, and I'm going to walk through it slowly and unload it piece by piece. It outlines the whole progression from beginning to end of the story that I'll tell you more details about in the next few slides. It starts 1967 with fundamental research going on outside of the laboratory. We jumped in about in the mid 70s and had a lot of fun doing basic research on this until about the mid 90s, and then realized that we could be applying this for the problem that I just told you about, and began applied research increasingly with partners, because we just did the chemistry, the basic chemistry part, and as things started to work and also not work like we thought, we had lots of help from other national labs, and engineers came in to turn our chemistry into a working process. Piloting and deployment started about 2008, and it goes on to this day, and well for another at least another 10 years at Savannah River Site. Okay, so that's the rough timeline. And again, in pictures on the left, lower left, we're showing the kind of molecules we've been playing with. We call them calyx crowns, and I'll get more into that later. The pilot plant we call the MCU, or Modular CSX Unit, at the Savannah River Site. CSSX, meaning caustic side solvent extraction. That's the name of the process that was tested in the pilot plant. They treated 7 million gallons in the pilot plant. In fact, at first they called it the pilot plant, but after a year they realized, hey, this is really working real well. This is part of our waste treatment program. So they kept on going. They kept this thing going from 2008 to 2000 for 10 years, about 2018. 7 million gallons they did. And now they've got the salt waste processing facility, which was in design and construction all through this. And now they've gone hot in 2022 and are employing our chemistry in there. All right, so I'm going to walk through this. Here's the whole timeline. Crown ethers were first reported in 1967, and that spurred an awful lot of research, because people immediately thought, well, this is very useful stuff. These were the first molecules that could actually bind alkali metal cations. A related class of molecules, and these are what we call macrocycles, large cyclic molecules. Calixarenes were first reported for cesium separation in 1983. A few years later, three scientists won Nobel Prize: Pedersen, Lane, and Cram. Late 80s, as you know, the Cold War ended, and then DOE looked at all the waste that we'd accumulated and the environmental contamination, and realized that there's a huge cleanup ahead. In fact, the Office of Environmental Management that grew out of this has had the second largest part of DOE's budget all this time. To this day, it's about $7 billion a year. An awful lot of research happened in the 10 years after that. Really, a lot of good early stage research was funded. For the next 10 years, it was more very applied and deployment oriented. But in that stage is when we came up with our chemistry. We came up with our process in about 1995 and 1998. We developed it. The process was selected at Savannah River for deployment in 2002. Yes, WPF, the salt waste processing facility, then went into design phase shortly after that. And to give you, well, you all know, you're not naive about how long it takes to implement nuclear technology. It went hot in 2022 and started design in about 2020 or 2003. So 2 decades from design to actual startup. $2 billion. Okay, let's see. Then we're perfectionists. We're never happy with the process. We came up with the next generation process, which is called next generation CSEX or NGS, next generation solvent. We came up with this chemistry. It works really about 100 times better. Good news is that they didn't have to change anything but chemicals in their plant. The original process, the CSEX process, got a decontamination factor of, it was designed for a decontamination factor of a modest 12 for cesium. It actually performed, sustained at 100 to 200, so they're quite happy with the process, working a lot better than it was designed. With an NGS, now it was sustained at DFs of 50,000, which was just quite amazing. The SWPF went hot 2022, and then they went hot with the CSEX. They're going to implement the next generation solvent then in about a year from now. That's the whole timeline. I walked all the way through it. Now you can all start, you can look at your cell phone and check your email. But I'll tell you in more detail what's going on in these steps that I just outlined. The NGS knocks years off the schedule. It performs so much better, they can actually raise the throughput, knock several years off of the schedule, and that saves billions of dollars. And with only about a $10 million investment, that's a really nice return on investment. I like to think that research pays off, and I think everybody in this room would like to agree with that. And here's some numbers to prove it. The waste, as I've explained, is mostly alkaline sodium nitrate with very little bit of cesium there. 40,000 times more sodium ions than cesium ions. So we're talking about pulling a needle out of a haystack. And not only that, but they want us to take 99.9975% of it out. So that's a real interesting engineering and chemistry and engineering problem. Well, when crown ethers came out, everybody thought, okay, here's some molecules that can bind alkali metals, so great, we ought to be able to get cesium. And sure enough, some of the larger crown ethers could bind cesium. And the one here, you can see these are cavities lined with oxygen atoms, ether oxygen atoms. This one has 7 oxygens, this has 8, this has 6. 7 was the magic number, and a lot of people did quite a bit of work looking at this one. But actually, these were not good enough. What was good enough were the calyx crowns, which was a hybrid molecule of 2 macrocycles. A calixarine, which is shown here in blue. This is the calixarine frame. And then a crown ether. So we have 2 macrocycles that are married together. So we call these calyx crowns. And they really did open doors. I wish we could say that we invented these, but they were reported by groups in Europe, and we credit them with really ingenious development. These are separation factors, and there's a little math to calculating those, but basically the numbers, you can read the numbers as follows. A number of 17,000, for example, would basically mean that cesium is extracted 17,000 times better than the sodium. Okay, so for the basic crown ethers, you see we have okay numbers, but they are really not good enough to get the needle out of the haystack. But when we got up into the above 10,000, now we're really talking about some really powerful selectivity. The calyx crown possesses a ready-made cavity for cesium, and that's why it gets the nice selectivity. This is from crystal structure reported in the literature. You can see the cesium fitting nicely in the crown ether cavity. You'll notice that the elixirine frame here is crowned twice, once on each side, so that we call this a bisque crown calyx. There are versions with just some single crowns, and we call them monocrown calyxes. The cesium fits in the mono and the bisque crowns the same way. If you turn that molecule, you put your eye in this along the screen and look down into the molecule, then you see the cesium sitting into the cavity, and you see a beautiful fit of cesium in the cavity. So here's what we call the complementarity principle that works. What's even more impressive is that cavity exists even when the cesium is not there. That's important. It's actually a vacuum. Water doesn't go in there, and so it's a very hungry molecule to have something sitting in there. Nature does abhor a vacuum, so that provides part of the driving force for pulling the cesium into the cavity. If you look at the outside of the whole complex, you see it's very globular and nicely soluble in organic solvents, which helps us with the solvent extraction. But there's one little issue here. The anion is not part of the binding. The molecule binds the cesium. The nitrate that's needed as a counter anion for the cesium is not bound. It's kind of in the outer part of the molecule. It's not accommodated. The cesium is almost buried. You can't even really see it. All right, so we've got calyx crowns, and they've got all this selectivity, so we're good to go, right? Well, we thought so, but we spent years after that learning a lot. The binding of the cesium ion by the calyx crown drives the extraction, but the co-extraction of the nitrate anion, now it's X in the diagram, and I'm going to show you, is highly unfavorable. We measured the thermodynamics that I'll be explaining in just a minute. We did it in an organic solvent, which is immiscible with water, 1,2-dichloroethane. Everything's nice and soluble. And we could do some really good fundamental experiments. This is the thermochemical diagram, and I'll walk you all the way through it. We start with aqueous cesium, which is the metal ion here, nitrate anion, X, and in the aqueous phase. And we're going to end up with a complex, very much just like I showed you, with the metal inside of the calyx and with the anion kind of sticking onto it. The steps are like this. The cesium and the anion transfer to the organic phase, and that is very costly to do because the metals really, the anions really like to be in aqueous solution. They like to be solvated by water. They don't like to be solvated by the organic solvent much. So you see these numbers have really high positive Gibbs energies of partitioning. Okay, but the binding of the crown of calyx to the cesium to form this positively charged cation is highly favorable, and that balances the unfavorable nature of the partitioning of the ions to the organic solvent. And then the electrostatic pairing of the nitrate with the cation complex is also favorable, and that helps the driving force. So that's the overall thing. The chemistry provides for the binding of the cesium cation by the calyx ground, but it doesn't really do anything about the anion. So the anion is a problem. So modifiers to the rescue. We're not going to just use the calyx crown alone because they don't work so well. Hydrogen bonding from alcohol molecules to nitrate can help drive the extraction. So we're going to add some alcohol modifiers to the solvent. And I'm going to show you some data that shows you how that works. So in the experiment, we added the calyx crown and to one of these ingredients, including the null case. And here we're plotting the distribution ratio for cesium, distribution ratio of 1, meaning that there's the same equal concentrations of the cesium in the organic phase as there are in the aqueous phase. So you want numbers that in your process to be greater than 1. In this experiment, it just illustrates the fact that, first of all, when you don't have any modifier, the distribution ratios are minuscule, almost can't even detect extraction of cesium. When you start adding polar molecules, you can start to get higher distribution ratios, stronger extraction. And when you get to alcohols, sorry, Herb. When you get to alcohols, there I did it again. You see that now we're bumping up the distribution ratios by 3 orders of magnitude. And here I credit my colleague Peter Bonison with coming up with some ingenious fluorinated structures that we actually ended up adopting in the process. Okay, so far I've just talked about the extraction part, getting the cesium into the solvent, but you don't have a process until you actually can strip it out and then recycle your solvent and then take the cesium on to your to the stream that goes into the vitrification process. So here's a cartoon showing what our initial hypothesis was. This is the calyx crown in a water immiscible solvent. This is the solvent cycle. Calyx crown extracting the cesium nitrate from the aqueous waste and then forming this cesium nitrate complex in the solvent. Then taking that solvent, contacting it with water, cesium nitrate comes out. We've demonstrated that and it works, but it's really not practical. It's a good idea in theory, but we ended up with something a lot better. But that's kind of the way science works, right? You have a hypothesis and test it, and if you're lucky, it works great right off the bat, but usually you're learning something. We've learned a lot, and let's fast forward from 1998 to 2015, in which we learned a lot. We had lots of iterative testing in collaboration with other national labs and universities. We had plenty of help and really good engineers inspired to help us. We made the first generation, the CSSX process work, and it was selected, as I mentioned. The next generation process was a lot better, and that was tested and now it's adopted for deployment at the SWPF. You can see these this hot cell test here with small contactors, and these are the big contactors that they used in the MCU, and very similar in the SWPF as well. Here's the solvent that we ended up with. It evolved over the years with lots and lots of learning. It's quite a complicated solvent, it looks like. The main ingredient, of course, is the calyxarine, and this is a mono-crown calyx that we call max calyx. And it's very soluble in kerosene. And we modify that with a Peter Bonison's magic modifier, which is fluorinated to give it a little bit stronger hydrogen bond donating. We call that CS7SV. And then here's an ingredient I didn't tell you about, because if I really told you how we learned about this, we have to take another hour and you'd fall asleep. So we'll skip that chapter, but let's suffice it to say that the process needs a lipophilic base in the solvent. We used triethylamine at first, but in the next generation solvent, we needed something more basic, so we turned to guanidines, and this is a trialkyl guanidine, triisodecyl guanidine. And that's all in a kerosene diluent isotope. So that's the solvent that we ended up with. It works great, MCU tested it, sustained DFs of 50,000 in the MCU. Very stable. The same solvent, they never disposed of the solvent. They just trimmed it all these years, for 10 years, kept it going. There's a weak ingredient. The suppressor is somewhat unstable, while the other ingredients are fairly robust. We learned we have to trim this one about every 3 months. Notice we just have a smidgen of this molecule in there. Only 3 millimolar makes the process work. Otherwise, it will not strip. Now even to this day, we're still playing with this chemistry for the SWPF deployment. We're going to raise the modifier concentration, and we're going to switch to a more stable suppressor, more stable quantity. In chemistry terms, this is the cycle, very similar to what I showed you. We have that alkaline tank waste with cesium, and potassium also gets extracted a little bit, 100 times weaker, but still some gets extracted. And nitrate is the main anion that comes along. This scrubbing step depicts potassium being scrubbed out. There's another important thing that happens. We also replace the nitrate with hydroxide equivalents. And what that does for us is it allows us to contact the solvent then with boric acid. And we're going to vitrify this in borosilicate. So we thought the engineers would be delighted to use, to have a stream of boric acid coming into that. They're finicky though, engineers. They still complain. They always complain. But we lowered the concentration to 10 millimolar, and they said, "Oh, okay, we'll use your boric acid." And that stripping is extremely efficient. We start with a p-value of 50 for this distribution ratio for cesium of 50 in extraction, and stripping it goes down to 10 to the -4th. So as if any of you've ever played with solvent extraction, you know you can design a very powerful flow sheet with that kind of extraction and stripping. Now, for your engineers, yes, we ended up with a real engineering flow sheet out of this that could be tested. I don't want you to have to strain your eyes and look at it all, but just suffice it to say that the chemistry diagram that I showed you was reduced to a real engineering flow sheet that then was used in the MCU. This is what was actually used. And this is the overview of the whole thing. Just everything that I've told you, the fundamental research going to the pilot plant, and then finally the salt waste processing facility. So that's the story. And I guess I get to say thanks to all the great people and great minds that made this possible. Over the years, we have well over 100 publications just on the cesium chemistry. 2 patents. Peter Bonison, Rick Stocklaven, and I started that off this early 2000 timeframe patents. And of course, inspiration and long hours in the lab. Leticia Delmo made NGS work. Jeff Bryan taught us about how the structural chemistry is working. Tatjana Levitska, Tammy Haverlock, Fred Sloop, and later Neil Williams and Nathan Besson did the lion's share of the laboratory work, and I'm certainly grateful to have been able to lead this team. Okay, so here we are basking in the glow of Ernie Moniz in 2013. The salt disposition team received the DOE Secretary Award, and there were 78 names on the plaque, and at least 10 times more people, contributed. You couldn't even recognize everybody that played an important role in this. And it's quite an experience to go from fundamental chemistry all the way to shaking Ernie Moniz's hand. Okay, so we've a lot to be proud of. That's my big story. Now I want to put this in the context of the tradition at Oak Ridge National Lab. We've really done a lot in separation science and technology, and let me start from the beginning. The Manhattan Project, and you can see under construction the graphite reactor and the hot cells next to it. And what people usually don't show you are the waste tanks. And that's kind of a harbinger of all the problems that we'd be encountering after the Cold War ended. And fortunately, at ORNL, we had only a tiny bit of waste compared to Hanford and Savannah River. And so we've closed those tanks now. Here's what the old timers called the pilot plant. The hot cells adjacent to the graphite reactor in 1998. You can see back here the reactors that played a lot of role in neutron science and isotope production over the years. These are now coming down, and I thought you'd like to see a picture of a couple of them coming down. This is the demolished low intensity test reactor. And then the bulk shielding reactor. Both of them are now down. I think they still have this central reactor part of it still. I think that's still there. They haven't dealt with it yet. This is about when I came to the lab. 4500 South. I spent most of my time there. This parking lot's kind of on a slope, and right out of grad school, my car was quite a jalopy, and I had to park on top of the hill so I could roll it down and start it to go home at night. Anyway, you can't see. We were behind the fence then, of course, and you can't see that very well in the diagram, but in the picture. But we're behind the fence, and this parking lot then was used to then build the new campus. And now here's the new campus. And of course, now we have to walk about a half a mile to get to work every day from the parking lot, because now the parking lots are way out on the periphery. Okay, and this is the chemical and material science building that we moved into in 2011. And okay, so that's sort of a quick tour of history and pictures. Of course, the original mission was a neutron and separations experiment. And so separations began as a tradition in the lab, a great strength over the years. But over the years, DOE's missions have expanded, so have its needs for separations. And here are some of the diverse impacts: subsurface contamination and separations, nuclear waste treatment, as I just told you about, isotope production. Now we're worried about critical materials and where they're going to come from, clean energy, nuclear fuel cycle, and decarbonization, CO2 removal. I'll tell you a little bit about each one. I can't delve into the chemistry of anything, but just to hint at what are some of these awesome accomplishments. First of all, the pilot plant produced some awesome processes that through 1988, it developed and executed what are now standard reprocessing technologies. First, the Purex process. 1949 was the first report on Purex that came out of ORNL. I think we can share some pride in coming up with that process for recovering plutonium and uranium from irradiated nuclear fuel. The Thorex process did the same, but for thorium fuels. And over a 35-year period, 2 metric tons of U-233, in fact, were recovered. And all this was done with an amazing molecule, very simple, tri-N-butyl phosphate, or TBP. I think it's the most famous extractant there is, and we can justly feel proud of having made use of this molecule in a productive way. Now, I've told you about Purex and Thorex. What you probably haven't heard of is the AMEX processes, or amine extraction from ore leachates. When I came into my group, Jack McDowell's group at the time, this group had developed the amine extraction chemistry for uranium recovery, and also it works well for molybdenum and vanadium. This is the standard chemistry now worldwide for this purpose. The Di-Topo process was invented and developed just down the hall from me. In fact, all these 3 processes were developed in the same wing of 4500 South where I worked. And just down the hall, Fred Hurst was coming up with what he called the Di-Topo process, that for recovering uranium from phosphoric acid. So we produce a lot of phosphate fertilizer in North Carolina and especially Florida. And there's uranium and there's also rare earths there as well. And Fred, the chemistry is rather difficult. Fred came up with the recipe to do that and develop the process, and it became the standard process worldwide for recovering uranium from phosphoric acid. In 1999, the price of uranium was no longer high enough to sustain the economics, and so the last plant closed. But now people are still talking about recovering uranium, and if the price gets any higher, you can probably expect that that process will be reanimated. Tall speed never really became a process, but it was highly influential. It was the use of aqueous phase complexants to control the selectivity of DEPA, di-2-ethylhexylphosphoric acid. And in so doing, you could recover americium and deuterium-3 from lanthanides. And so that opened the door for a tremendous amount of chemistry that people are still looking at to this day for actinide recovery from high-level waste, so that you could actually get almost all the actinides out of high-level waste, which would make the burden on repositories much less. Okay. Let's talk about isotope production a little bit. ORNLs have had a 75-year history here in isotope production, and the Manhattan Project was not even over yet when people started to think that isotopes would be a mission. And sure enough, they started shipping radionuclides for medical uses almost immediately after the war. In the 1960s, there was over 100,000 shipments of radioisotopes annually. ORNL, became sort of became famous for isotope shipments, and nowadays we're focused on isotopes not available in the private sector. Here's a menu of the kind of isotopes that are now in production and being produced, in production and being produced. In production for distribution, sale and distribution. Quite a list. I should mention that one of the big missions of the Radiochemical Engineering Development Center, which the picture of which was in the previous slide, was to produce the trans-curium elements for research and especially medical applications. So one of their big products is californium-252, but they've distributed trans-curiums up through fermium for fundamental research for well since the 60s. Isotopes have also played a critical role in national security. And I think the most famous example is saving New York City. And now I'm sure there are fans of the 50s sci-fi flicks in this room. And of course, we grew up watching the originals, right? So you remember this one? The Beast from 20,000 Fathoms? Well, okay. Gee, now I'm gonna have to, oh, you remember it? Okay, you know, okay. So, well, the Beast was awakened by, contamination in the Arctic. It came out of the Arctic and decided to come down and attack New York City. And so created a lot of havoc. And so what saved the day was ORNL's, well, unidentified isotope. But our hero crawled to the top of the roller coaster in Coney Island with a black box that said Oak Ridge. And he fires this isotope at the monster, and the isotope worked its magic, and New York City was saved. So anyway, Oak Ridge's isotope production and the separations, of course, that went into it have had a long history, and of course with major national security implications. Okay, let's only a couple more slides here. Now, present day problem is decarbonization, and people are actually seriously looking at how you could recover CO2 from the atmosphere by direct air capture. And this is a big research area. We know how to do it fairly well from stacks, but people are actually talking about how you could get it out of the air. And there, up here, you see a crazy looking molecule that we call bis-aminoguanidine, where this kind of grew out of the guanidine chemistry that we were looking at. But the magic of this one is it binds carbonate, and it binds it strongly enough that it can pull the CO2 out of the atmosphere and crystallize it so you can filter it off. And what's even better is that only with mild heating you can liberate the CO2 from it. So now there's this process, and industry has commercialized it, and we're going to see if it can be scaled up. Nice process. As you know, alkaline solutions, caustic soda will pull CO2, form sodium carbonate, but you have to heat the heck out of it, calcine it to get the drive off the CO2. So this mild process really has some advantages. Nowadays, we're worried about where's the lithium going to come from for all our electric vehicles? Where are the rare earths going to come from for the traction motors in our EVs and wind turbines and stuff like that? And a lot has been has transpired over the last 10 years, dozen years, in fact, as we've kind of waken up to the fact that we really aren't producing these elements that are needed for these high-tech applications. And 2011, DOE produced its first critical material strategy. They just now, 2 weeks ago, issued the 2023 assessment of critical minerals and materials. And this diagram is the matrix published therein, in which on the y-axis we're plotting the importance to energy technologies versus the supply risk. Supply risk, of course, has a lot of geopolitical implications. If the metals are coming from a friendly country, friendly countries, and not any supply issues, that would have low supply risk. Lithium, you can see, is in the upper right-hand corner. It's one of the ones that we're really worrying about. Nickel. We produce precious little lithium and nickel in our country, although we have resources. Same with cobalt. Rare earths always get up in here in the criticality. Dysprosium, neodymium, and praseodymium, and terbium for magnets, the very powerful magnets that we need in our traction motors, and also for the speakers, so Steve can play guitar. And also uranium, you see, is up here. Oh, by the way, a few years ago, we concluded a nice project on uranium recovery from seawater. Shanghai led that, and we came up with some very improved materials that will recover uranium, not yet economically from seawater, but doing a fairly nice job. Okay, so all of these elements require separations if we're going to have supply chains. And so therein lies the need for a lot of separation research. That's now ongoing in the Critical Materials Institute as one centralized research program. We're working on molecules like these, which find rare earths very efficiently, and we're learning a lot about how they work. Unlike where we were 30 years ago with our initial cesium chemistry, we have unbelievable computational tools now. We can see these molecules and model them with our molecular dynamics calculations. Here's what one version of our molecules look like when they complex the rare earths. We have a nice process that's evolving now that we think that could actually upend the 60-year-old entrenched technology as a kind of a prophecy for future, along with other applications and isotope separations and carbon capture from the atmosphere. So we certainly do have a lot to be proud of. We've changed the world, and we're still doing so. We're going to continue doing so. Looked at my big story and some examples of separation science and technology at ORNL. So anyway, I will take your softball questions now.
Do not do the waste or thing where it's down here. One of these times, take everything back into the glass.
Well, boy, that's a good question. We're still kind of scratching our heads about that, but each site dealt with their own problems and their own regulatory environment with the state agencies and tribal issues. And so in the negotiations with the state and regulatory agencies, and I think the tribal nations up there, they decided on a very conservative approach, and that's roughly how they did. So I think influenced a lot by political considerations and negotiations with regulators and stakeholders. Savannah River had a different climate in which to operate, and so they argued successfully that they could take their 99.99% of the decontaminated high-level waste and put that into some cementitious waste form. There's their saltstone.
So where does the saltstone go?
It goes in those vaults.
Oh, permanently, never leaves the site?
Well, I don't see how they could leave the site as big as they are, but I'd say that's pretty permanent, Fred. They will sit there into perpetuity, and I'm kind of wondering if sea level rises 100 feet in the next.
And so maybe that's a reason Hanford might want glass which can be transported. Savannah River accepted the saltstone.
Sid,
Yeah, Albert Weinberg was a big fan of the thorium fuel cycle. And as little as I know about separation science, the separation of protactinium would be very helpful to getting the fuel cycle going. Is that something that separation science can approach?
Yes, it is that's a good question. Of course, in the thorax process, they looked at this kind of chemistry, and people nowadays that are looking at the thorium fuel cycle are dealing with this. And one issue is production of U-232, which is a real hard gamma emitter, and once you get some of that in there, it's very, very difficult to manipulate the waste. So and that has a lot to do with how you deal with protactinium.
Well, is any work being done on that now?
To my knowledge, at the lab right now, I don't know.
Back in the 60s, I think there was some work by chemists trying to do that, and they were somewhat successful. But if we got the thorium fuel cycle going, that would really help with our physical uranium problem we've got now, where we're going bonkers with some crazy speed.
Yes, and well, you're kind of singing to the choir on that one. There are many fans of the thorium fuel cycle, and I think industry is even seriously paying attention to it now.
Yeah, I see where DOE spending some money now looking at aqueous reprocessing again. I see where they funded several ARPA.
Yes.
Is there something new or great about this technology now, or the separations that can bring down that cost of that, back end of the fuel cycle? All these separations you have to go through, waste products and all, they're very expensive to deal with.
Well, that's a good question. Well, it goes to some things near and dear to our hearts. Yeah, we would like to have a sustainable fuel cycle, and the back end is the key to that. And so what do we do? There's lots of chemistry being looked at around the world for this, and ARPA-E is funding some research and scale-up testing with some industries like Curio and ORNL, but they're not really talking about much more than recovering the uranium, the remaining enriched uranium from the HALEU advanced fuel. So if you use the new more enriched fuel that they call HALEU, then you're going to have more U-235 in the used nuclear fuel, and that makes it even more important to recover the uranium. That is where their attention is focused, not so much on anything else. So at the moment, I think the paradigm is to just grab the uranium and leave everything else for disposal. But that's not, to me, a sustainable fuel cycle. And then we can talk about that for a long time.
Steve, do we have any?
We have one question. On one of your earlier slides, you showed the path of the fission products. There one, and John Gunning is wondering where they go. That is, except for the cesium. The other fission products.
Oh. Okay, so most of the fission, well, there are three layers in the tanks, right? There's the hydrolytic sludge that forms when you make the high level waste alkaline. So almost all the higher valent elements are in that sludge. And so it's really hot stuff. In fact, they've been running at Savannah River since 1995 to vitrify just the sludge. So they take the sludge, wash out some bulk constituents, and then left with basically all the trues and most of the fission products. So then they've been taking that right into the VIT plant, which is called a Defense Waste Processing Facility. They've been making canisters of that waste ever since. Okay, what's left is the salt waste, and there are really only two fission products of concern in the salt waste. So that's the cesium-137, and I haven't mentioned 135, but you know that's a long-lived cesium isotope. So they're there, and traces of strontium-90. Most of the strontium-90 still gets precipitated too, because strontium carbonate and strontium hydroxide are fairly insoluble. So that ends up mostly in the sludge too. There's some trace actinides that are there. We don't know what form they're in. They could be colloidal, but they need to come out too. So the answer to your question is most of the fission products have ended up in the sludge, which is going into the glass.
Earl,
Bruce, you mentioned rare earth, separation of rare earths. Well, where are the sources for those in the United States, and what are the uses for some of these rare earths?
Well, that's really,
besides magnets.
yeah, that's a starter to a good long seminar. I have a seminar. You'll have to invite me back. But the answer to your question is okay. You've heard in the news media, oh, all these woes of rare earths. You know, next to China, the U.S. is the second largest producer of rare earths in the world. We ship 43,000 metric tons of rare earth concentrate every year. The difficulty is we don't have a supply chain. So it can't, right now, it's not going anywhere except to China. So we mine or we concentrate it and we send it to China because we don't have a way to do the separation here in the US. So that's quite disconcerting. That's going to change though, not too far in the future, as the mining company MP Materials that runs the Mountain Pass mine in California that's shipping out all this concentrate. They are also beginning to ship separated neodymium praseodymium. We call it NdPr. That is an ingredient for magnets. So they're beginning to actually do the separation and send out that product. They were doing that back in 2015, but by non-competitive process, and that was when the mine was owned by Molycorp. They went out of business because they were losing money. But now, I think we're going to be back in business. The new plant is operating, is being built by MP Materials in cooperation with General Motors in Texas, and they will actually start to manufacture magnets for EV purposes. So there's a lot of hope.
First, so many questions. First, I'd like to answer Carolyn's question. Is saying she has what's the resource? I'd say depends on two things. What's the price? And how good is your separation technology, which that's you. So learned wonders today about separation.
Yep, you got it.
I'm amazed. You know, I've been a really skeptical of direct air capture because of its parasitic load. I mean, what's the point of running an engine to pull if the energy going in also has a carbon, right? So it's like a self-licking ice cream cone. So how low with your techniques or similar techniques to yours, how low could they get the parasitic load of running that process? Because right now it's let's see, the conventional like amine capture, carbon CCS with amines, it's like 33% parasitic load, and that's the electricity of the plant. 33%
Yeah.
is DOE thinks they might hit 25% one day. And you know, the industry boosters think, oh, we could do 20%, but 20% is terrible. It means you have to build a fifth power plant for every 4 you've got operating. So what do you think direct air capture could operate at in terms of a parasitic load? How good could it get with these funny molecules I just learned about?
Well, I'm still employed by ORNL. So I think I'll stay away from the politics. I'm just a mere technology provider. So, but you raise really excellent points, and personally, I'm with you.
By the way, I also think coal ash is an overlooked resource. We've got piles of it all over the country, and some of the coal ash, especially the stuff that came from North Dakota, Montana, uraniferous lignites. And the ash is more uranium energy in it than you got from burning lignite. So there's coal ash around, and nature's already done the separations, so to speak.
Yeah, but trouble is, the coal ash is a vitreous waste form.
Yeah.
And the darn stuff's hard to leach.
Yeah.
And it has rare earths there. I mean, DOE's piling hundreds of millions of dollars into looking at recovery of rare earths from
our brother take
coal ash.
this year.
Yeah, okay, so you know all about that. So yeah. And there are technologies now at the demonstration stage to show that you can do it technically. Now, whether that'll compete with MP Materials processing 8% rare earth oxide ore versus a few hundred parts per million of uranium 0.01%.
If you're lucky,
If you're lucky.
Yeah.
And so the economic scale of grade, and so that's it's a tough road to hoe, but technically we're able to do it.
Yeah.
Yeah, phosphate rock is another example. There's rare earths in that, there's uranium in that.
Yep.
And the technologies are there, but man, you like you say, you got to produce it at price equivalent to the market price. So you're stuck.
We have enough time for a quick question from Zoom.
The question is, could you kindly provide your insights on how AI and ML are expected to shape the role of separation science in the near future?
In 1 minute. In 1 minute. Happy to, because of 1 minute is about all I know. Look, you know, one way is that we don't, separations, I told you about a very elegant separation. That was about 35 years of applied research, and even a couple decades before that of fundamental research. What AI can do is shorten that time span for developing new extractants with amazing new selectivity. It will help in the design of new molecules that will separate, you know, rares, lithium, gallium, uranium, whatever it is, and from whatever matrix. So not only designing the molecules, but designing the processes that will work. So what I think is a good answer to your question is that it's going to compress the time frame for developing the new chemistries for the separations.
Well, we've used up our question and answer time, but if there are more questions after we finish, you can approach Bruce and ask them that. So I want to thank you for your nice survey of excellent survey of what you've done, what separations at ORNL is in the past, present, and the future. It's probably the best description I've heard of separation history and the future. So thank you.
Oh, yeah.
So how much